meeting here in Milan. This was like in 2004. During Salone, and basically I showed Reed around Salone. He had never been to the furniture fair before, and it was my sort of like home turf, and I showed him around, and it was it was close to an embarrassment because it was so insanely boring. There was just like new plastic chairs, and Reed was like, so what's new about that? And I was always like in this position of going like, you know, it's a casino chair. It's really exciting. And then we only spent like 48 hours here. Had like a Prada meeting, and everything we did in technology back then seemed incredibly exciting and very cutting edge and everything. And this world of furniture just seemed so dull and so boring. And then we sat in Cardona, where the Malpensa Express leaves, in this cafe on the trackside, and basically talked about doing, you know, let's do something in furniture that's disruptive. Also because it's such a good opportunity, because there is nothing. It's all kind of boring plastic chairs and the next couch and whatever. And we scribbled this thing onto a napkin, just considering like why don't we start growing structures in the computer? Why don't we make structures that are sort of flexible, parametric, and then push them straight to a machine and like basically use a machine like a 3D printer. And then we actually also right there coined the term breeding tables, because we needed some sort of like working title for this little side project. And we thought, why don't we, let's breed tables, let's call it breeding tables. And that stuck. And basically what we built then was a sort of process which back then seemed absolutely mad. Now all of this seems much more feasible and realistic. But basically the idea was to write software that is purpose specific, software that is not universal, but that can only do one thing, and that would be to draw tables. And also software that doesn't allow you to draw things that the machinery cannot manufacture. So basically, there was this feedback loop of everything: the laser cutting machine, the bending machine, all the machine parameters, like, you know, how, yeah, you can only bend to a certain degree. Like if you have 8mm steel, you can do like 90 degrees, you can do 100 degrees, but you can't go any further. So we restricted the tools of this sort of CAD software to not allow the user to draw anything that would bend the steel further than what the machine can do. And this is a quick sort of animation that shows you how it works. You can put in the table height, the table width, the length, the leg size, and then there's all these sort of genes. So it's almost like describing a physical object in a set of genes, and then obviously you can manipulate these genes, and they have a relationship to each other. So as you draw this thing, as you set it up, there's a basic geometry that consists of these cutting planes, first construction planes, then cutting planes, and all the aspects here, all these different parameters, they can all be tweaked. And you will never get collisions because there's genetic algorithms that basically sort out the cross bracing in a way that it never collides. In the same way, the branches of a tree will never actually touch. They will always grow in a way that there's no collisions. And then we unfold in the computer. The laser cutter cuts the contour, and then it's physically folded back up by a brake bending machine that receives, so the worker on the brake bending machine receives information on the actual pieces he works on, because it's laser engraved and tells him what to bend first, what to bend second. The whole thing is painted. Tabletop. And shipping. And basically this software enabled us to draw a huge variety of tables that could be manufactured by just pressing a button, like literally going like print. And pressing that button would mean you send the data to these machines, to the laser cutter, to the bending machine, and just do it without having to think about the engineering aspects behind it. Because normally when you design something, you spend so much time on figuring out, like, you know, how does the machine work. You learn a lot in the process, but once your design is finished and you've done this one definitive design, all this knowledge just stays in your head, and over time you start forgetting it. And basically, this is an attempt to capture knowledge about machinery, about processes, but also about a certain idea of sort of unleashed aesthetics, like where you also like where you're able to calculate a lot of options with the algorithms and actually pick and choose things you like, and from a very wide variation. And another interesting thing is, since you have this genetic code, you can obviously also join genetic codes. You can do actual breeding. You say, I like this and I like that, and the two of you, maybe you know, team up and have some offspring. And then from that offspring, you can pick and choose and say, I like this, I like that. This we did only for ourselves. So we were the operators of the software. We didn't give this away to third parties. The idea here was not to let the consumer or the sort of the layman, the civilians take any control. It was just for us to draw tables very quickly and to basically be able to manufacture a very wide variety of tables. However, when we did this, we already considered a future scenario in which we would actually be able to, you know, give control over the whole process to the end user. But back then, we launched it in 2007 or 6 or 7, 2006 here, first in Cologne, then at Salone, and it seemed quite distant technologically to actually do it through the web, because there was no way of doing a 3D environment online back then. You would have to write like an executable, people would have to install software on their computers and so on. So there was a couple of issues there that were yet to be solved. This is a few little side tables generated with the breeding table software. This is how we develop. Like there's always some welding and you know, cutting and angle grinding involved. It's never that this beautiful diagram you see in the end is in the beginning always like a very rough sketch, and then we immediately get busy and hang out with the people who actually make the machines or own the machines and learn everything. This is, for example, the brake bending equipment, and the thing on the top right is the matrix. This is the stamp, and basically the sheet steel gets laid flat onto the matrix, and then this stamp sword comes down, and the sheet metal bends up. Another thing that we later on integrated into breeding tables was stress testing, because obviously if you, with AutoCAD or like any CAD software, you can draw things that will instantly collapse after you actually build them. So you can build 5-kilometer high towers or, you know, whatever, chairs that instantly collapse if somebody sits on it. And so basically we started integrating stress testing into the software that, as you draw, basically puts loads on the pieces you draw and decides whether or not it would withstand the weight of 2 people on the table. That's sort of the benchmark. And then we just increase certain features. So if it fails, like up there, we would increase either the width of the piece, or we would move the geometry around, and then an algorithm would basically attack that problem and continuously spit out new options until it reaches a point where the structure becomes sound and stable. There's still a bit of hand labor involved. So this is when the individual components of the table are finished and bent, they're being painted, and then we assemble them in the studio. This is our old studio, like the basement of our old studio. And then you get these structures, 8mm steel. And here you can see this is a prototype where we just blatantly welded welded stuff together instead of joining it like later with a nice little bend feature and screws and stuff. So this is a very early prototype, 2006. And then later on we went on to resolve all these details, how to attach these components, like from where to screw. So the software actually decides from which side the screws go in, because we teach the software basically there's a virtual eye. So the software always tries to place connectors in places you don't immediately see. But something like that, it sounds incredibly easy to tell. Like if any of you were working in our studio on this, and I would tell you like, make sure you don't see the screws. Done. But the computer, to explain to a piece of software, put the screws out of human sight, is an incredibly complicating task. So you have to break down these things in a way that you can actually code them, that you can actually teach a computer what it means not to see a screw. And that's a month-long effort sometimes. Something that between humans takes like 2 minutes. Sometimes if you have to explain it to a computer, it takes months.